Okay. In order to use OpenMP, we can use directives, runtime routines, or environment variables. All we have to do. Oh, they're telling me that there was some problem with sound before. So let's go back. Here to slide 3 to describe what OpenMP is. OpenMP stands for Open Multiprocessing. It's just an application programming interface for developing parallel programs for shared memory architecture. Shared memory architectures are just most of the machines that we have nowadays. Any laptop, even any smartphone that we have is a multi-core machine where all the cores have access to the same memory. There are 3 main components of OpenMP: the compiler directives, the runtime library routines, and the environment variables. The standard specifies C, C++, and Fortran directives and API. And although we have here a lot of information in this tutorial, you can go to the official website, openmp.org, where you will find the official specification of the language, of the API, sorry, many examples, tutorials, and a lot of documentation. So the reason for using OpenMP, well, as I said before, we have multi-core machines. What you want to use, if you just run your code without using OpenMP or using any other parallelization technique, you're just going to use one core. So you want to use all of them if possible, right? So OpenMP is very useful for that. Second point is that OpenMP is very easy. Compared to all the other technologies that we have for parallel programming, OpenMP is almost trivial to use. And third point is just OpenMP is widely supported. All the main compilers out there in the market support OpenMP up to a certain degree, certain level. So it's very portable. You can write your code and compile it everywhere. So OpenMP is going to allow you to create and destroy threads in a very easy way. Compared to other approaches like pthreads, OpenMP is trivial. You can assign and distribute work to those threads, and you can also specify which data is shared and which data is private. As I said, since all the cores are accessing the same memory, you have to have ways to say this piece of data in the memory is shared by all threads, or I want this piece of data to be just specific to one thread, or just all of them to have independent copies of that data. In order to use OpenMP, we can use directives, runtime routines, and environment variables. All we have to do, for example, in this case for C, is to include the omp.h, the header file. This is for Fortran, and also we had to pass an extra flag to the compiler, which in the case of Intel is -OpenMP. Otherwise, the compiler will complain. If you have GCC, the flag is -F OpenMP. So the architecture of OpenMP is just, well, the elements here is just, the main one is the data. The data can be shared or private. The shared data is all threads can access that data. By default, you can consider that all the data, if you don't specify anything, is going to be shared by all the threads that you create when the data has been already declared. Private data is only accessible by the thread that owns that data. Okay? You can move data from shared memory or shared data to private data, and that is transparent for the programmer. You don't have to worry about it. The OpenMP environment or runtime will do it for you. All the programs in OpenMP start with a single process, which is the master process. So essentially, every OpenMP program, if you're not using MPI, is a serial code at the beginning. This master thread will run in serial mode until it finds a parallel region construct. We'll see what this is in the next slides, so don't worry about it. But remember, it's just we only have one thread until we find the parallel region. After the parallel region, we create several threads. Okay. That doesn't mean that when we create threads, those threads still doing nothing. Okay. You have to assign tasks. You have to give work, or give things to do to those threads. So all we have right now is idle threads. All the threads in the parallel region, once they start working in the parallel region, we will run at the same time, which doesn't mean that they are going to be executing exactly the same instruction at the same time. But they will run at the same time the same statements in the parallel region, unless we specify different workloads for all those threads. And once we finish the parallel region, the threads synchronize and terminate. That doesn't mean that we destroy the threads, because that would be highly inefficient. Once you create threads, the threads remain alive until the end of execution. Just so, because creating threads takes some time, some cycles, so it will be a waste of cycles to create threads, destroy threads at the end of the parallel region, when potentially you have to create them again. Okay, the OpenMP leaves the threads there alive, even though they are not doing anything. And the threads will communicate using global memory or shared memory, because since they have all access to that, they're all sharing the same address space. And you have to be careful here, because if they're all sharing the same memory, that means that you can potentially have race conditions, meaning threads updating data, share data when they don't have to update it. You have to be able to use mutual exclusion with atomic or barriers, or however you want to do it, to avoid these race conditions. It's also important to know that it's not a good idea to have many of these atomic regions or critical sections. You have to reduce them, because what happens when you create one of these regions is just only one thread will have access, or will be running at that point to have access to memory, meaning that all the other threads will be waiting until that thread finishes. Okay, so that's a clear bottleneck. I will show you how to potentially reduce that with different techniques in OpenMP. And this is the OpenMP syntax. It's fairly easy. All the constructs start with, I'm going to talk more about the C part, but the Fortran is very similar. They all start with pragma OMP, and then you have the construct. We'll see what that construct is in the next slides. For example, we have here how to create a parallel region. We create pragma OpenMP OMP, and then we specify parallel. What that means is that in this case, the master process, which when it finds this instruction, it creates a number of threads. Okay. If we don't specify anything, it will depend on our environment, how many threads will be created. In this case, since we are specifying 4, the master process will create 4 threads. Okay? And those threads will, all those 4 threads will continue the execution immediately, the instructions after that, all at the same time. So these are the constructs of OpenMP. We have parallel control structures like the parallel directive, which is the critical thing, is the one that actually creates threads. And then we have the parallel control for work sharing. As I said, once you create the parallel region, all the threads will execute the same instructions. That's not something that you want, because what you would do in that case is just to run the same thing n times if you have n threads. So what you want to do is to split your workload into chunks and send those chunks to the different threads. The easiest way to do that is just the parallel do, or parallel for in C. Another critical point is the data environment, as we have always said, which is how to declare which is shared and what is private. The synchronization, that is what I already mentioned, how to synchronize tasks, how to ensure that only one thread is accessing a portion of the code at a given time. And we also have the runtime functions, or the environment variables that allow us to set number of threads that we want to use, to get the thread number. Also, the environment allows to do those kind of stuff. So, as you saw, OpenMP directives are just comments in the source code. Those kind of comments. The compiler will take those comments and say, hey, this comment means that I have to create threads here. Okay, and it will do it. Parallel regions are marked by enclosing parallel directives. This is more clear in Fortran than it is in C. As you can see here in the Fortran example, we are going to have $OpenMP parallel and $OMP end parallel. Everything that happens between the OMP parallel, OMP and OMP end parallel, it will be a parallel region where several threads will run in parallel. Okay. In C, C++, we don't have that end parallel. We just have pragma OMP, so you have to use the C syntax to create the same kind of behavior. We also have here an example of how to use the work sharing construct with pragma OMP parallel for before a for loop. What we are saying is just create. I'm going to explain this a little bit more because many people don't understand. They use it, but they don't really understand what it is. When you do pragma OMP parallel for right before a for loop, what you are doing is this. With pragma OMP parallel, you are creating the threads. Okay. Then with pragma OMP for, what you are doing is just for those threads that I just created, I'm going to split the workload that I have in my for loop and share and distribute that workload into the threads. Okay? We could have two different instructions here, pragma OMP parallel and pragma OMP for. We'll do the same thing. Okay? If you don't do the parallel, you're not doing anything here. Okay? And if you don't do the for, you're just doing the same thing n times. Okay? So this is another simple example of how parallel regions look like in C and Fortran. In C, we have the C syntax to specify the block that this OMP parallel applies to. And for Fortran, we have to specify OMP parallel, OMP, and OMP end parallel. For example, this is a C code that shows how to create a 10-thread parallel region. We just define an array here of 1,000 doubles. We specify that we are going to create 10 threads with OMP set num threads. After line 2, we still don't have any threads. We only have the master one. Okay? Is line 3 the one that creates the 10 threads that we have specified in line 2? So all that, well, here in lines 5 and 6, all we have is just 10 threads running the same thing 10 times, basically. So how do I make this mouse? So each of them will get their ID, and then we'll call the same function with different parameters, okay? But it's important to remember here that since we are not using any for or any task, all we have is 10 tasks potentially doing the same thing. So you have to be careful with that. There are two main modes for OpenMP for how to create threads. One is static, which is just we have a fixed number of threads that is set with the OMP non-threads environment variable. And we can also use the function called OMP set non-threads, which is what we just saw in the previous sample. Or we can specify non-threads, as we saw earlier today. And you always want to use one of these three ways, okay? And there's also a dynamic mode. I never used it before, so I don't even know how this works. But basically what you do here is just let the operating system decide how to create threads, how many threads are going to be created. This is never a good idea. And we are going to see later on today for profiling why this is not a good idea. But basically, you want to take control of your environment. You want to know what you're running, and you want to take, because you want to take advantage of the machine that you have, okay? So we already talked a little bit about this. This is how we create threads, and we, using a for loop, how we distribute the task between the threads. In this case, I split the parallel and the for in the, I forgot an OpenMP here. Anyway, that happens. The first one for C should be pragma OMP parallel. In this case, we are creating the number of threads according to our environment. And this for loop that we have here, we are distributing each of the statements or of the iterations of the loop between the threads that we just created. Okay? We can see again the difference in syntax between Fortran and C, how in Fortran we had to specify the end of each region, while in C we don't have to specify anything at all. The previous example that we saw here in slide 15, we can do it this way. Again, I forgot pragma OMP parallel for. I hate when that happens, because then you are going to copy paste and you're not going to realize what you're doing. But it should be pragma OMP parallel for in the C example. This is exactly the same thing, and this is the most common OMP syntax, okay? Where you just collapse the two instructions just into one. I just wanted to make sure that you understood the difference between putting parallel and putting for. Another different construct for OpenMP is sections. With sections, what we achieve, the idea behind them is that you create a sections block, and inside of that block, you create independent sections. Each section is just going to be executed by one thread, and only one thread. This was originally used to create tasks, the idea of tasks that was later introduced in OpenMP 3.0. It's quite powerful, but the code can be a little bit messy, not the cleanest code that we can have nowadays with tasking. But this is very interesting when you have two completely different things to execute by two different threads. Okay, they don't have anything in common. It's very easy to do this kind of stuff. I'm going to skip this part. There are different clauses in OpenMP that control the behavior of OpenMP directives. We already saw some of them, which is the number of threads that we are going to create. But there are directives for the type of scheduling that we are using. How scheduling in this case means how the tasks or the workload is distributed and is distributed and assigned to the different threads. Okay, it can be static, dynamic, guide, and runtime. There are also directives for data scope, if it's private, share, or default behavior. For the initialization of this data, first private, last private copying, etc. We can decide if a parallel region is going to be parallelized or not. This is not that common, but imagine you have a for loop that you want to parallelize, and that for loop, you don't know how many iterations you have in that for loop. Meaning sometimes you are going to have 4 iterations, sometimes you are going to have 300 iterations. Well, when you have 4 iterations, you probably don't want to create threads. Especially the for loop is very small if you only have 1 or 2 instructions. Why? Because the time for creating the task and assigning the task to the threads is going to take longer than actually running the 4 iterations in serial mode. So you want to create an if clause in that parallel for to decide if number of iterations smaller than, I don't know, 100, for example, I run this in serial mode. Otherwise, I create threads and run it in parallel. I guess, yeah, there are scenarios where that can be useful. This is one of the confusing things of OpenMP. Every time you're playing OpenMP, you have to go and explain people what static and dynamic and guide and everything is. The reality is that don't worry too much about it. What this schedule means is just how, as I said before, how the chunks of work that you have are distributed to the threads, okay? Static means that when I'm compiling my code, I already know how those chunks are going to be distributed to the threads. Dynamic changes based on which thread finishes earlier than other threads. And guided is also even more complicated. But as I said, don't worry too much about it. Unless you're really worried about performance, just go for dynamic or static and don't worry about it, okay? The difference is going to be very small. If you're really worried, all you have to do is to to run different tests and see which one works better for you. Usually for performance, if you have a really good work balance, load balance, static is going to give you the best performance. But again, it will depend on your case, okay? Again, here I gave a little bit more information about how these scheduling options work. This is more for your reference, but the idea that you have to take from here is that static has the lowest overhead, while dynamic is kind of medium. The other 2 options don't really use them. But you can play with static and dynamic and see which one works better for you if you're really worried about your performance, okay? And this is how you specify your scheduling in OpenMP. In this case is Fortran, but the same thing for C++ or C. All you do is just after your OMP parallel do or for C and C++, you specify a schedule, and then you specify which one you want. In this case, we are saying static, and the extra argument says the size of the chunk. Okay, 16 in this case. So what this 16 will do is just, as I said, it will create chunks of size 16 to distribute those chunks among the threads. So thread 0 will take iterations from 1 to 16, thread 1 to 17 to 32, thread 2 to from 33 to 48, and so on. That is already defined that before the code starts running. So that's why it has so little overhead. Okay. This is critical in OpenMP since we have shared memory. Is how you specify how data behaves. What is shared data? What is private data? And the other instructions are how private data is initialized, how private data looks like once all the threads have finished, if it has to look like something. For that, we have share, private, first private, and last private, and we also have reductions. Okay. By default, the variables that have been already defined are shared. And this is one of the few things that the OpenMP standard defines, okay? So if at the beginning of your code you define an integer, that integer is going to be shared by all the threads that are created after that definition. So you have to be really careful with that. All the global variables are also shared, as you can imagine. Everything that is declared once the threads have been created, it's private to the thread. So if your thread is calling one function, all the variables inside that function are private to that thread. Okay. Of course, all these can be changed by using the default clause. Also, the default clause is very interesting because it allows you to say, hey, forget about default. I can say default none. Once I do default none, all I have to do, well, you have to specify the scope of each single variable that is going to be accessed by the threads. So if you have race conditions in your code, the best thing you can do is go specify default none and think about each individual variable that you have, how you should declare it. Okay, it's really good for debugging. It takes some time, but it helps you find race conditions. Also, when you're learning OpenMP, it is really good. It helps you understand how everything works. As I said, a shared variable is shared by all the threads. And private variables are just local to each thread. So in this example that we have here, we are saying that forget about what was shared before or anything like that, but by using default none. So forget about defaults. I want to make in this sample A, B, C, and N share. Okay? And I, which is the index that I'm using for the loop and the index I'm using for accessing those arrays, is going to be private. Usually, well, the index, the iterator that you have for iterating over the loops has to be private. Okay? So all threads in this case are going to have access to the same A, B, and C, and also N. But each thread will have its own private copy of I. Instead of loop, it should say here, thread. So you have to be really careful here, because since they are all sharing the same arrays, A, B, and C, you don't want two threads accessing the same index of the arrays at the same time. You can do it for read operations, but you don't want two threads doing two writes at the same time, or one write and one read at the same time. That's where you have the race conditions. Okay, and those are the things that you have to control, and it gets quite tricky. It's difficult to find. Yep, we have a question here.
When you do things like nested loops, can't you see, like in the example, like why you need to not make the iterator private, or to say share part of the iteration of the loop with another thread?
I guess you can find scenarios where you want to do that, but I don't know if I would tell you go ahead and do it. You can do things like that, that's for sure. I'm thinking of when that could be useful. But yeah, can you? Yes. And if you cannot do it with the iterator, you create a variable that acts as an iterator. Okay, and that can be shared. But yeah, I don't know when that could be useful. But if it's useful, yeah, you can do things like that. This is another example that where each thread is going to need its own copy of this temp variable, because otherwise they will, they will share that variable, and we will never have the right value in there. Imagine if you had two threads using the same temp, a shared temp variable, when they are using different indexes I for accessing A and B, we will get different values for temp that will be overwritten by other thread. Okay, so that has to be private. A first private here that we have here will create what? Before saying that, is just a private variable. The value that it has when it's first accessed is undefined. Okay, so here, if in line 4, if we wanted to do something like A equals temp, we don't know the value that temp has in that case, even though maybe temp was assigned outside of the loop. Okay, but the value inside of the loop, once it's private, is undefined. We can say, hey, this had a value before, I want you to keep it. So what you do for that is to define that variable as a first private. Okay, so whatever you had before the parallel section, parallel region, you keep the value. So each thread will create its own copy of temp with that previous value. And you can do something similar if you want to keep the value after the parallel region. You can use the last private that will give you the last logical value of temp after the parallel region. Okay? Especially first private is very, very common. It's very useful. I'm going to start rushing a little bit. So reductions are operations that combine multiple elements into to form a single result. The variable that accumulates the result is called a reduction variable. The syntax is a little bit funny. You decide, in this case, we are saying that the variable a sum is going to accumulate the result of all those adds operations, while a prod will accumulate all the results of the multiplication. Okay. After the loop, the master thread will collect all the results, and you will only have one value for each of those variables. These are the different levels of synchronization that we have. The two main ones are critical and atomic. So what we are doing with this is just avoid race conditions. Okay. What happens inside of a critical region is that only one thread can be inside of that region at any particular time. No two threads can be there. Okay. When one thread is here, for example, in line 6, 7, or 8, all the other threads will have to be waiting in line 4 until that thread finishes in line 9. Okay. Atomic is a little bit. It's a kind of a simplification. It only works for this kind of instruction that you see here for atomic operations. Okay. But both are basically the same. Only one thread can be executed in line 7 on the right block, while all the other threads will be waiting on line 6. Okay. We also have barriers to synchronize threads, meaning I'm not going to continue my execution until all the other threads reach this particular line, this particular barrier here, line 6. Okay. This might be useful for some kind of load balancing or synchronization of tasks. Logs are really powerful, and I feel that most of the people don't use them because they don't even know they exist. Critical sections or critical and atomic that we saw before have a problem that is just you are blocking potentially a large block of your code so that only one thread can be there. And imagine that you are working on vectors, on arrays, and you have like chunks of those arrays, and you know that one thread is going to only be working in one section of the array or in this iteration, it's only accessing one element of the array, while other threads can be accessing other elements of the array, okay? In that case, those two threads are independent. But if you create a critical section, they have to wait, okay? So what you can do is to create kind of independent logs for those chunks, saying, hey, I'm going to work on this chunk of the array. I'm setting the log for this array. No other thread can access that part of the array while I'm working on it. If you're working on another part of the array, go ahead. I don't care about that, okay? So logs are very useful for that, very powerful. The only problem that they have is that they use quite a lot of memory. You can run some tests of how many logs you can create on Stampede, and you run out of memory quickly. Let's skip that. So this gives you an idea of the overhead of using these kind of instructions. For the logs, you will get 300 cycles for setting and setting the log, which is quite high compared to the other ones. But since you are using the logs for specific areas, you don't have other threads potentially waiting for this particular thread to do something. So even though the overhead is higher, your performance might be much better, okay? So in general, yeah, if you can use logs, use logs. That's all I want to say. Stop using critical and barriers. Many of the OpenMP constructs have implicit barriers at the end of the construct. For example, for loops. You can avoid that if it's really necessary with the nowait clause. In this case, once a thread has finished everything the thread had to do, it will continue. It will go to do whatever it had to do after this for loop, or if it has nothing else to do, it will just go to the end of the parallel region. These are the different environment variables that you can set to specify the number of threads or the schedule that you want to use. The most important one here is OMP non-threads. For example, in Stampede, if you are going to use OpenMP, you want to say, since each one of our nodes has 16 cores, you want to set OMP non-threads equals 16 potentially. Okay. That will also depend on your machine or where you're running this, even your code. OpenMP also offers some timers, which are nicer to use than the one provided by C, C++. I've even seen people using OpenMP just for the timers, which is quite an interesting concept. All you have to do is OMP_get_wtime, and you assign that to variables, and that's all. So then you only have to subtract the start from end, and you get the time from that particular part of the code. It's a very simple time. Yeah.
Is the timer for the whole program, or is it for a thread?
For whatever you want to. That depends on when you're calling that, right? You can call it within the thread, or you can call it in the level of the program. So then you play with what's shared, what is private.
Depends on whether or not you're in a parallel region.
The thing is that if you call it within a parallel region, you will have 8 copies of this, right? This is the wall time. It's not the CPU time that is giving you wall time. But yeah, you can do something. You can do things like that for timing your independent threads. Compared to the syntax for C for timing is, yeah, this is so easy. We already saw the non-threads before, how to specify the number of threads that you're creating. And we go to OpenMP 3.0. The main thing of OpenMP 3.0 is, as I said before, we had sections in OpenMP 1 and 2. And with sections, you can make that each thread runs a completely different thing. Not just for loops, but just completely different parts of the code. But the syntax was a little bit strange. With tasks, this is extremely strongly simplified. Let's go directly to the syntax. All we have here is pragma OMP task, and that's it. That will, if you do this within a parallel region, it will create independent tasks, one task in this case. Okay, so it's very interesting. Imagine you put this inside. You can even simulate a for loop with this. You create a pragma OMP parallel, then you create a for loop. Inside the for loop, you don't have the for in the OpenMP clause, but inside of the for loop, you create pragma OMP task. Basically, what you're doing is that each iteration of the for loop is one task. So you're doing the same thing that you were doing before. Okay? That gives you an idea of how to create tasks. Task can be anything. So a task, you can go into an if-else block. The if can create a task. The else can create a different task. This is very interesting when you have, different things, completely different things to be done in your code. Okay. And the code is really nice. Yeah.
Is the task executed as soon as you create it, or is it put in some kind of queue?
There is a queue. If there are free tasks, if there are free threads, they will start immediately. But otherwise, there is a queue. Yeah. Once you start using this, it's very cool. And you realize that OpenMP is not just what you thought it was. OpenMP is much more than that. Okay? It starts feeling a little bit like simplified MPI, kind of. Simplified MPI in shared memory. It's a really fun concept. Oh, another thing that no one knows about, or many people don't know about this, that you can use iterators. Many people think that you can only use OpenMP parallel for with integers. Well, if you have something like a vector in C++ and you're using the iterator for going from begin to end, you can parallelize that code the same way. Because just an iterator is just basically you know what you're going to have. So it's very easy for OpenMP to split that into parts, okay? But yeah, many people don't know about this, and that was an addition in OpenMP 3.0. Not all the iterators are supported, only these random access iterators. If you go to the specification of what a random access iterator is in C++, you will realize that most of the iterators that you actually know are valid for this, okay? But there are, I think there are 11 different types of iterators in C++. Most of them cannot even be used, so I don't even know why they exist. But anyway, I'm not going to talk much about C++. This is how you do. Maps are a little bit tricky, so this is how you do with maps. But this is how you. This is a way of creating tasks and distributing those tasks to threads. You want to have a parallel region, and you're going to have only with this OMP single, nowait, only one thread, the master one, will go into this for loop, okay? In the for loop, what we are going to do is to create threads, to create tasks. And we are going to assign those tasks to the threads that we already created in line 1, okay? Why we do the OpenMP single? Well, if we don't do the OpenMP single, what we are going to have is 16 threads, if we have 16 threads, going into the for loop, creating tasks, okay? So you're going to have 16 times what you wanted to do. So the idea behind task is that only one thread creates the tasks, okay? So you don't have duplicated stuff. And just perfect timing, we go to OpenMP 4.0. And this is where OpenMP gets goes out of control. I've been talking a lot about shared memory architectures in OpenMP. Well, OpenMP 4.0 kind of says, hey, I'm not just shared memory, I'm much more than that. And it allows you to use distributed memory, kind of like shared memory. That's the reality behind OpenMP 4.0. And to be honest, it looks like the future of OpenMP is going that way. So OpenMP 4.0 is going to allow you to use accelerators. For example, here we have the mic, Intel Xeon Phi, from the host. And what is that? Well, the host, which is your normal node, will run your code, and you will specify that at some point you want to, that massive, usually for loop that you have, you want to run it on the Intel Xeon Phi, because instead of 16 cores, you have 60 with 4 threads per core, 240 logical cores instead of 16. That's a lot of cores that you have there for free, basically. So you want to use them. So OpenMP allows you to do that, to my code that is in the host, send it to the mic, send my data to the mic, and run there. So remember that the memory that you have on the mic and the memory that you have on the node, on the host, those are different memories, okay? So we don't have shared memory anymore. But still, OpenMP is creating this illusion somehow that you have shared memory. You still have to transfer the data, okay? But yeah, we just went from shared memory to distributed memory in OpenMP 4.0. It also allows, it's not just shared memory, now it's also allowing to specify vectorization. What is vectorization? Well, most of the modern processors have a vector unit. A vector unit is a unit, it's a specific part of your processor that allows you to run many operations at the same time. Single operations like subtractions, multiplications, so on. And it's called vectorization because it works in vectors, basically. With OpenMP, you can specify that you want something to be vectorized. This is something that Intel already had with their own syntax. But now with OpenMP, they are trying to standardize a way to specify, hey, this thing is going to be vectorized. Not only that, is that this function that I have can be vectorized, okay? So again, OpenMP is expanding and expanding. It's just not just this shared memory threading stuff. Now it's much more than that. This is how we declare a function, or this is how we use vectorization in OpenMP 4. We can declare functions and say that these functions can be vectorized, meaning that they can be called from a vector operation. We can also say that they cannot be called if there is a branch, an if-else instruction. Why? Because if-else don't play nicely with vectorization, okay? In that case, yeah, it's just that it's not going to vectorize. It's quite complicated. We have an expert in computer architecture here that can tell us more about it. But yeah, I want to say about vectorization is that I would say it's still quite a work in progress. The documentation is not very nice. It's very confusing for some specifics of vectorization. And some examples are really difficult to follow. So don't worry too much about it. And it's just to give you an idea. Yep.
When did this capability start?
OpenMP?
No, the vectorization.
In OpenMP. It was like, well, the first, like they started talking about it several years ago. First compiler supporting this, I think Intel was supporting this like almost 2 years ago, but very experimental. Now it's fully supported. But that being said, you specify your function as something that you want to vectorize, and the compiler is going to tell you, I'm not going to vectorize that no matter what, because I don't like it. You can even force it to say, you don't like it, I don't like you, do whatever I'm telling you to do, and you can vectorize it, okay? So yeah, vectorization is still, I would say, it's going to improve quite a lot in the next years. And we're going to finish with the accelerator part. The idea behind OpenMP is that they want to support any accelerator that you have. That means that they want to support GPUs, they want to support the mic, they want to support FPGAs. So the standard that they have defined allows to specify things that are just very specific to GPUs, like teams of tasks, which is something that if you know GPUs, it's something common in that architecture. That might not make any sense on the mic, but it doesn't matter. That's what the specification says. Then it doesn't mean that if you write right now an OpenMP code, you will be able to offload that into the GPU. Because if you have NVIDIA GPUs, it will be up to NVIDIA to decide what they support and what they don't support. And right now, they are not very keen on supporting this. But we'll see the future. FPGA, even worse. But the mic are fully supported. All you have to do to use accelerators is just to specify that you are using an accelerator with each Pragma OMP target. And you have to transfer the data. You transfer the data by saying Pragma OMP target data. Okay, that's all you're doing. Somehow it's just, it feels like adding extra attributes to your data, the same way that we were saying before, share or private or whatever. Now we are kind of defining this data as this data is going to be transferred to the mic. Okay? This compared to the other alternatives or the other option that we have for sending data to the mic, the interway, it doesn't get any easier than this. Okay? The syntax is very clean. It's very easy to remember. Even Intel is moving this way. And this is what it looks like a real example. We are just saying that we are using the device 0 in this case because we have one mic. So we use the device 0. We are mapping the variable A from the host to the mic. And then we are going to retrieve the variable B, which is going to be our result from the mic to the host. Okay? And that is how you define it here, the first line. And other than that, it's just you are just saying that you are going to run this on the mic with Pragma OMP target. And that's it. All this will run on the other stuff will run on the host. As I said, compared to what we had before, this is very easy. And you can guess what they are trying to do with this kind of syntax and where they are going, and the future looks actually quite interesting for this kind of extension of OpenMP. And that's all. We just went 10 minutes over the time, considering that we started 10 minutes late. That's it for OpenMP. We had now some one lab that you guys sorry. All you have to do in this lab is just follow the slides. You have the slides on our website. So just follow the slides. And if you have questions also for people in the chat, just let us know and we'll be happy to help. But all the instructions are there. I guess you guys all know how to connect to Stampede. If not, here we have a reminder how to do it and where to find the lab. Okay? So we have like half an hour for this lab, Jason. And the next session starts at what time? In 45 minutes or something?
Schedule says that from 10 to 10:30 is the lab.
Yep.
Then have a break from 10:30 to 10:45.
Okay, so the next section will start at 10:45, so in 35 minutes. So again, feel free to follow the lab. I'll be here to answer questions and to help you with that. Okay, thank you very much.
I think they consider it someone else's problem.
Oh, there's a surprise.
can't see you back.
All right, everybody, we're going to start the hybrid lecture right now. I'm going to introduce Kent Millfield. He's going to be presenting, and we'll also have a lab here in a little bit as well. So, just do this slideshow
right here. Okay, hello, my name is Kent Millfield, and this morning we're going to try and get finished with pneumatic control and hybrid applications in a lab. Hopefully this will only take about 45 minutes for the pneumatic control hybrid applications presentation, but it may extend a little bit longer. But first, what we want to do is there is, need to explain both of these. Pneumatic control, which we'll get into, and then exactly what is a hybrid application. But first of all, we want to get a really good, clear picture of what we mean by an MPI process and an OpenMP process and what's happening there. So hardware-wise, we got to look at that, and we got to look at what we mean by a hybrid application in terms of software. So in terms of hardware, when you submit a IB run, when you submit a code to be executed, and it's an MPI code, you do two things. One, you tell it the number of tasks that you're going to want with the -n option. Okay, so that's one thing. So what is, when you specify, say, -n16, that you want 16 tasks, what happens is that number is divided by 16, the number of cores on a node, and the number of nodes that you get for how many tasks that you want is determined by dividing 16 into it if you just have the -n option. So -n32, divide that by 16, and you get 2 nodes. Okay, so two things are done there. Now, when you're running your MPI application, the other thing that's done, of course, is that you use IB run. Okay, and IB run looks at the number of tasks that you're going to use in the environment, and it actually starts off multiple processes, just like multiple processes depending upon the number of tasks, or equal to the number of tasks that you're adding. So if you have an application, we're just going to say the executable is a.out, and you say IB run a.out, what is really occurring behind the scenes is that you are executing 16 different processes in the background. And then those eventually hook up and you can run MPI across them. Now, these different processes on a node will execute on the different cores. Okay, 16 cores on a node, you ask for 16 tasks, you get 16 processes running there. Those processes are running in their own memory environment. They have an address of space associated to each one of those tasks, and that's only its memory that it can access. It can't see what the other task is doing or access that memory. So you'll have task 0 here, 1 here. It has its memory allocation and memory address space, and it can only see that. If you run, and when they need to communicate information, they do that through MPI. This task that's running here on this core does MPI send over here. This guy does receive and gets that information. Okay, so it's important to understand that underneath the covers, that's all that's being done in MPI is a.out is instantiated as processes on the node and on that single node. And if you ask for 32 tasks, it would run 16 on one node and 16 on the other, and they would communicate through the network, those two different nodes. On the system, on a particular node, it would communicate on node. It does it through some shortcuts, some nice efficient ways to use shared memory on the node. Okay, but in essence, each of those a.outs that get executed have their own memory space that they work in. Okay, so what about OpenMP? OpenMP, you can only run on a node. You create an a.out. You do that by, when you create your OpenMP application, use -OpenMP on the compile line, and it then knows that you have OpenMP directives in there, And when you launch that a.out, it's just a process that starts. That process, the main process that starts, is the serial part in there, and that's also called the master thread. When you get to a parallel region, it forks multiple threads. Those multiple threads are executing across these other cores in here. Okay, the operating system makes the assignment for where they run. Just like in MPI over here, it's making the assignment where those a.outs are run. And so behind the scenes, what happens when you run an OpenMP and a.out and it's forking threads is that the operating system has control and distributes them across the different cores there. So the important thing is OpenMP, you have your forking threads within the application, within the a.out. Those different threads have access to all the same memory. So if one of the threads actually allocates some memory, the other threads can see that and access that. So it's no problem, okay? So those are the two main different types of parallel paradigms that are going on. So why should we want anything more? Well, if you look over here at the MPI, nowadays we have 16 cores. We run on a node, we run 16 tasks. And when you do that, of course, there's a lot of communication going on, a lot of calls going on. If you have to run, if each of these cores has to communicate off node with to another node, then that's a lot of different MPI sends and receives. So that's a lot of messaging going on. You have to have buffer space for that. What happens when you go to many core? When you go up to 32, when you go up to 60? Well, you may not want as many tasks on a node. And what you might then think about doing is instead of having 16 tasks, you might think, oh, why don't I run one task? And then underneath that task, I run OpenMP within the same code. And what happens? I have that one a.out that's an MPI code, and I run multiple threads underneath that. Okay. Those threads share the same memory space. They can then, you can have sending a message from inside there to say another node as one aggregated send. Okay, so MPI, if you partition your space, memory space onto say 16 different tasks, you have to partition that up. Each one of these guys has to do communication, say with other nodes. It makes sense that if you're starting to have say 60 cores per node, it makes sense to have one or a few MPI tasks, and inside those MPI tasks, they are doing the OpenMP, okay? That OpenMP has the aggregated memory space that you needed for all those cores. It aggregates what it needs, and when you need to send it, it's one big message as opposed to a lot of small messages. So that's very helpful, why you would do that. So that's sort of the hardware view of what's going on. What about the software side? And the software side, how do you do this inside of a code? You know, you're running MPI and OpenMP. Well, in terms of compiling the code, you would still use the MPI F90 or MPI CC, and now you would just simply include the minus OpenMP on that command line. So that's the thing about compiling it. In terms of actually what the code's all about, the way it's done is, the way to think about it is that an MPI task, just a regular a.out, encapsulates some parallel regions in it that you program with your OpenMP directives. So this basically looks like you do an MPI init. In this case, you would do a underscore thread, and you'll be able to see this in the lab, what that exact call is, and it's a little bit complicated. We're not going to get into those details. It's been set up for you, but basically you do an MPI init, do some MPI calls in the program, and do an MPI finalize. You then get inside the code, you can then put a parallel region, an OpenMP parallel region. Here we have the OpenMP parallel region and the end of that region. You can do your MPI calls, of course, outside. This is the process, or what you would think of as the master thread now, coming down here, forking new threads, and then releasing those threads and coming back to a serial region. Now, inside the OpenMP parallel, you can do MPI calls. You can do multiple calls. That doesn't seem reasonable. What you'd say is, if I'm thread 0 or if I'm thread 1, do the communication for me. But more generally, what we see in these codes is that you have an MPI calls out here and then parallel regions without the MPI calls in there, okay? And all the complications of this is about how you would do that inside a parallel region. But most of the calls that the way you see most programming done these days is the MPI call is done here by one task out here by the master, the thread, you might say. Then there's parallel region, maybe then you come to the end, and then you do some MPI calls or something else, another parallel region, and you do not see that often the MPI calls within the parallel region. So that makes it quite simple to use. Outside, you have the MPI stuff, and usually you have interspersed in there the parallel regions that are OpenMP, that are sharing the memory on the node. So, typical definition of a hybrid application, it is an MPI, and then underneath there's a shared memory model, OpenMP, P threads, and other types of mechanisms like that. The OpenMP and P threads are the more direct way that people do this, that, you know, the language it's not done by the compiler. You have to specify the parallelism with the OpenMP or the P threads, okay? And of course, these are run on multi-core systems. Some people go to a lot of work on the systems that say 16 or less cores per node, and they find out that it really doesn't run much faster. MPI is pretty efficient in terms of doing the messaging on node, and it actually comes out to scaling that people are interested, why people are interested in using hybrid applications. Because on the mic, when you're up to 60 using 60 cores, you don't want a task running on each one of those. So it's these days, it's a scaling to many cores that is actually changing things. So now we've covered what a hybrid application is. The part that we didn't really discuss much is how and where are these processes or threads executed. And actually, it involves a little bit more than just placing it. It also involves where it's assigning memory, and we'll see that. So the concept of a non-uniform memory access is sort of maybe new to you, and maybe you don't know much about it, but up here, we just have one big memory area storage up there, and I don't see any non-uniformity. Memory looks uniform there. But on our nodes here, it's not uniform, and we'll see how that is. And of course, that makes life a little bit more complicated. Not so much when you're using all the cores on a node, but when you're using fewer of the cores on a node for each process, or you are doing hybrid. That's when it starts to make much more sense to worry about using this. And here's an example, a hardware picture of what we were talking about. Over here on the left, we have a pure PI application running on the system, and we talked about having 16 tasks running on 16 cores. Okay, two things here. Number one is, what are these two boxes? Okay, these are the two different sockets on a node. That is, we have two different chips on the node. Each one of these has 8 cores. Okay, So it's not just one big chip with 16 cores when you're running your application on Stampede. You're actually running on 2 different sockets. Okay, each one of these sockets has memory associated with it. Okay, on this one we show memory out to the left. That is connected to the chip via a memory controller here at high speed. And so we also have memory over on the other controller, on the other socket or chip, and it's connected to that. Now, we call these systems, we call these systems shared memory. So if I'm a task running over here, normally if I'm going to use memory, it gets put over here on my quote local memory. If there's not enough space or various reasons, it could possibly put it over here on the memory associated with this other socket over here. And if it's doing that, the connection from this task here wanting memory over here is through interprocessor communication. Okay, that's these blue lines here. You have a controller for the memory over here. The sum of these two is about say 80 gigabytes per second. You can get 40 from here, 40 from here in terms of memory bandwidth. Okay, and the link through here is a little bit slower than that. Okay, so number one, doing memory, getting memory from over here may be a little bit slower, but it also has to take a hop through the interprocessor communication. Okay, so, oops. So now what we really see on a node is that we have non-uniform memory access. If I'm a task here and I'm getting memory from this memory that's associated with my chip, then it's one speed. If it's over here on the other process, on the other chip's memory, I can have access. It's a uniform memory access space there, but it's going to be a little bit slower. Okay, so the real thing that's happening for the operating system, it's doing 2 things. It's going to put a task either on this socket or this socket, and then there's a memory policy it's going to have by default, and it's used by default. And whenever a task not allocates the memory, but whenever it starts using the memory and says, hey, I really got to you have this memory, that's when the page that it's using is assigned to the local, say the local memory, and it tries to do it in the most efficient way. But that's not always the fastest. It's like valet service. You're guaranteed parking, but boy, when you go park it on, when that valet guy comes up on a busy day, he has to go scramble and find you parking space. Well, that's what the operating system has to do. It has to find places to put your memory, and it has a normal policy. But if you run out of memory on this side, it will push it over there, and things will be a little bit slower. Okay, so over here is an example to the far right of the way codes are sometimes run, hybrid codes. They would specify that they wanted one task to run on that node, and in that task, then they would do parallel. It's a hybrid code. Inside, they would fork, say 16, actually the OpenMP num threads would be 16. The A.out gets started for that MPI run on this particular node. Then in the parallel region, it says, oh, I'm going to fork 16 threads. Actually, you have the one thread, the master, going, and you're really forking 15 more. And so that's how it's done. What works even better, and you see how codes are run, is that on each of the sockets, they have an MPI task run, and it will just use the number of threads equivalent to the number of cores on that particular socket. So that's the picture of running hybrid codes on our system. And of course, if you had 4 sockets, you might have 4 MPI threads. 4 MPI tasks, and then threads to cover all the cores in that particular socket. So some of the things about this, using NUMA control, the idea is we want to control how the memory might be positioned for arrays that you're using, and where those initial, say, MPI tasks start, and then where all the threads run. Now, what is pretty much symmetric is that if you run threads on a particular socket, it really doesn't matter which core they're using. There's no asymmetry in that, except possibly core 0 that might be running the daemons, okay, or that might be connected to the network interface, okay. So generally, when you're talking about threads and you don't give any NUMA control on those, they will, this operating system is good about positioning them there. However, it will not be necessarily, the operating system may not know where to position your MPI task. If I have, say, I want 2 MPI tasks, the operating system may say, oh, it's just a process to me. I'll put 1 here and 1 here, as opposed to 1 here and 1 over here. And so that's the thing about running hybrid, is to be able to control this and then let your threads, they will just automatically inherit the policy of the task, the MPI task, and execute there. So if you say, oh, I want you to execute on this particular socket here, any of them, but I want you to MPI task execute here, then the threads will go, okay, when it's doing the threads, it'll just go any place on these, and it can be shuffled around. And we'll talk about how to even be more specific about this. So the important thing is that you, with NUMA control, will have access to where the tasks are positioned, and even the threads. It's a little bit more complicated, and the memory allocation, how that's going to be done. And we'll look here shortly and see how that's done. Again, the important part about NUMA operations is that you make assignments of processes to cores, and that the memory allocation assigned by memory policy. So that's the memory. It's not really memory allocation. It's the memory, when it starts to be used, is assigned to a particular memory or what sockets memory. Okay, so how do you do this? If you don't do anything, the operating system has default policies and tries to do a good job of that. Can it do a good job of it? Maybe not so good. I mean, you have to consider what we're doing here. We have an HPC center, we have HPC nodes, and they're running CentOS operating system. And that operating system was actually designed for workstations and IT space. It really, the OS was not designed for HPC computing. So in the background, it's just trying to do the things that are nice and good for IT and desktops, not necessarily for HPC systems. And so to gain some of that back, when we run these hybrid applications, we have to use NUMA control and to do that. So how do you do this? Let's step back up one level and say, what are the different ways that you can do this? So you can run an a.out serial code or MPI. You could go to the node and sit there, and you can do a NUMA command. If you know the IP of that process you launched, you have to own it, and you could tell it to run it on a different socket. You can tell it you want to run it on a specific core, okay? And so that's very helpful, that having run it, you can force it to change, okay? So that's very powerful. You can do it at the process execution or at the process launch. You say NUMA control, some options, a.out, and when the operating system begins to execute that a.out, it looks at the NUMA control, or the NUMA control is controlling it, launches that process, and adheres to the options that you specify. You can also do that within the code. Okay. And for OpenMP, if you want to control that very specifically in terms of which core you execute, you actually need to do that inside your code at the thread level. Okay. Because inside the code is where you launch you do the fork on those threads. So it makes sense that if you want direct access, you have to specify to assignment to particular cores. You have to, in the OpenMP, get your thread ID and use the API and tell it which core you want it to execute on. Okay, so you're in the code, you got to do that. Otherwise, if you just say, I'm on this socket and this is where I specified my OpenMP task to run, then if you do a parallel region inside the hybrid code, it says, oh, I'm going to inherit from the MPI task, and that said any place on the node, and I'll any place on that socket, and I'll run on any core in that socket. Okay, so you are allowed to do that. And here's the basic NUMA control syntax is specifically NUMA control, the different options, and then your executable. Okay. What are these different options? Options, part of the arguments for these are either a socket number, here's socket 0, or socket 1. Now, I'm going to change language on you a little bit. I'm going to start using the NUMA language in that they call this a node and they call this a node. Okay. Hardware-wise, the node is that big case that has both of these in there with the disk and everything. But when you read the man page or other things about NUMA control, they talk about a socket being a node. Okay, so it's very careful when you go looking out there at the documentation to realize that they're in NUMA land, node is a socket. So this is node 0, this is node 1 over here, and the core numbers are 0 through 7 over here on Stampede and 8 through 15. Okay, that's on the Stampede compute node. Okay, Intel does something very interesting that you could even change this in the BIOS. And what they have done, if you're on the front end, very similar nodes, 0's here, 1's here, 2's here, 3's here, they alternate back and forth round robin. Okay, so you have to be careful, and it's actually a BIOS setting, and you can change the BIOS and have it so it's sequentially on a socket, these numbers, or that it's round robin, you know, across each of them. So, and there are different reasons for setting that up. We're not going to go into all those. So what you do in terms of process affinity, or you might say binding, is that you could use a socket reference for binding a process, and you could also do a core reference and assign it specifically to cores on there. Okay, in terms of memory policy, it only has to do with a socket reference. There are 2 of them, and that's it. Okay. Here are the different commands. Well, let's first look at the socket affinity and then core affinity. Up here, the command would NUMA control. They're all the same, and you can say -n, and you specify the socket that you want it to run on, or both of them. If you say I don't care, run on the socket, or socket 0 or socket 1, do both. But the usual situation is you'll have one task running on 0 socket, and then the other task or A.out running on the other socket. Okay, or you could get in a detail with your NUMA control. You have A.out you want, you can specify one or multiple cores. Okay, yes.
Do you need the curly braces if you specify multiples?
I'm so used to doing one, I honestly don't know. I think, I'm embarrassed to say, I don't know. I'll find out. I don't think you do, but I'm not sure. Good question. Memory policy, what you do is specify -L for local, and that means that wherever that process or that thread is running, it's going to put its memory when it's used or first accessed on that local memory there. Okay, if it runs out of space, it'll go put it someplace else. Okay, what you can do is say I want to run interleaved. That means that if I'm going through a big long array of space and and accessing that on my process for the first time, and when I hit a need for it, it will say, okay, I'm going to allocate a page of memory, 4096 bytes, and I'm going to put it on your local memory. Okay, as you're going through there, it comes along and says, after you get 4096 bytes of accessing and you access the next one, or next section, it says, oh, he needs a new page. I'm going to assign it to the other memory on the other socket. Okay, and that's what interleave does. It says your first request goes to this one. Your next request of using that memory, you could have allocated, a gazillion someplace up here, but it's where you start using it, and that will be pushed, to the other memory. So you in essence round robin how you're doing the assignment of the memory out there. Okay, and then you have a preferred. And you can say, oh, I just want it, this is meant for mainly bigger systems that have 4 sockets, 6 sockets, 8 sockets. You can say that you prefer certain sockets to push that memory to, okay, or avoid certain ones, by not including it. Okay. The important one down here is memory bind, and that not all the details are put up there. It says only allocate on this socket. Okay, so that has 2 consequences. One, if you can't get any more memory on that socket, it's going to abort on you. Okay, if you run out of memory. How could that happen? Let's say you are doing a lot of I/O, tons of I/O, and you have these buffer space there. And what happens then is, well, not in this case, but let's say you try and use too much, then the code's going to die. Okay. The other important thing that this does is that it frees up memory that is used by I/O buffers. Okay. Up here, if you're doing, say, local or preferred, when it runs out of memory, say on socket 0, it'll push it over to another socket's memory. Okay, no problem there. But it doesn't do anything else. Okay, so let's say you do a lot of I/O and you're using up a lot of buffer space in that situation. What's going to happen is it will fall over if it runs out of space to running on other nodes. Okay, not other nodes, other nodes, but on the other sockets. Okay, and so your code might run slower because it's trying to pick up memory on a different socket because you have a lot of I/O buffers there. What happens in this -M is it says, hey, if you have I/O buffers, I'm going to keep requesting, and you remove the buffers for me. You're not using them. You'll have to create them again. And I'm going to allocate that space on that particular socket or on that particular node. And so you're guaranteed to get your space. It's going to push other things off, in particular those buffers. And that's the good news, because you won't get into this degraded mode. And it may not even be your fault. If the person before you was using I/O buffer spaces and he did not remove his files, the system, it's an IT system, says, I don't care. I'm going to keep these buffer spaces. You come on to the node. And now all of a sudden you have problems and that your code's running slower because of these IO buffers that were left there. Actually, on our system, we clean them off. But that's why I went through the scenario of you using a lot of buffer space and then not needing it, okay? So there's reasons to have that -m. So how does the operating system handle this, handle affinity? Basically, for any process or any thread out there, it has a string of bits that it keeps in memory that's a map for where that process or thread could run. So the operating system is keeping track of bits here in this map. We have 16 cores up here. We have 16 different bits. The first 16 in this case, in the orange here, go to this orange socket up here. And so, and of course, there we go. So if I'm just going to use make one assignment, a CPU assignment on this, and I say, oh, I just want my process, whether it be this or my thread, in this case it's 0, and I want it to go to core 0 up here. You make that assignment and the operating system has this big old long string here and it says, okay, this guy says that I should run it here and only here, okay? That's sort of a binding, you know, really hardcore binding. Now what you could do is specify, whoops, I'm missing the other one. It's not coming up. Okay. The other thing that you could do is you can say I want 0 and I want 0 to also be assigned to, there it is. I can say I want 0 to be assigned to 3 up here. Okay. So in first case, I said assign it to 0. The next case, I said assign it to core 3. Okay. And now you could, and it's not coming out right. So I could also specify I want my process down here or my thread to be on 1 or 0 and 3, in which case it'll do both, okay? It will have a 1 here and a 1 here, and when the operating, when it goes to run, it will say you can run on 0 or you can run on 3, okay? And what happens though if you ask for a socket or a node? What the operating system does is puts 1 in all of these. And when it says, oh, I've got to do something with this process because I got the OS, it needs to come in and do something, I got to move it out and move it back in. It says that you can, when all these are 1s here, that you can execute this process or this thread on any of the cores in that node or socket. Okay, so what's the general scenario or strategy that users have for using NUMA? So important thing is that if you have MPI tasks, that you spread them evenly across the different nodes here. If you when you execute on those threads, or you have the thread level executing, they will take on the different cores and execute on those according to the load, okay? And if you want to get in more detail, you could actually do the assignments within the code to run on those on particular cores. And what about the memory policy? MPI local is the safest. The fastest would be the -m. For SMP codes, you're just mainly the OpenMP part or just SMP code period. Interleave may be the best for large completely shared. That is when a thread actually accesses all of the memory, then in which case sometimes it's good just to do the interleave and spread it all out. Normally, if you have the threads accessing local memory or local just sections of arrays only, then of course the local is going to be better. And then once allocated, the memory structure is fixed. You cannot change the policy and move that. You'd have to remove it and then reallocate it and touch it to do that change. So again, to go back into how these things are launched and what's happening, normally you have a single MPI task launched on a socket or actually on the hardware node, and that guy becomes the master thread. And you use NUMA control options to specify which socket you want that to run on. And then, as we said before, when you fork a region in OpenMP, a parallel region, these threads inherit the policy of the process that is running that master thread at A.out. So how is this done in a batch script? You have your code here that you compiled with MPI-CC or MPI-fort with the minus OpenMP option, and you have constructed it as an OpenMP code. And so once you have that compiled, it's A.out. In your batch script up here, we now are using a -n option saying, I want these many nodes. And then what the system does is looks and says, how many threads, I mean, not how many threads, how many tasks did you want? And it says, oh, you want 6 tasks, and he wants 6 nodes. So I'm going to put 1 task on each node. So that's how you get that going there. And then inside your script, you mentioned that, oh, I want 16 threads on each A.out that's run. Then down here, you turn off all the different possibilities of the MPI setting up your doing its own thing with affinity. Remember, I said inside the code, you have an API and you can set affinity there. MPI does this and in the background. It's once you get going someplace, it will sometimes assign a task to a particular core, not a socket. You know, it'll assign it to a core. And now when you run your OpenMP underneath and you say, I want 16 threads, those 16 threads are going to run on 1 core. And so, you know, instead of your code running 16 times faster, it's going to be running really slow. Okay, and so you turn off the MPI things that are trying to set affinity with these environment variables up here. And now what's happening down here in the IB run, we know what's happening to this part over here now. The IB run is going to launch this command and the rest of this line 16 times, or 6 times, 1 on each of the nodes, and it has a single NUMA control right here for all of them. And now what we're going to do is say we want interleave all for each of these A.outs. So you're going to launch A.out on one of your hardware nodes, another, and you're going to do 6 of those. And the IB run on each one of those is going to do a NUMA -I all A.out. Okay, and it's going to run that on it. And underneath, you are going to get your 16 threads like we showed previously. Here's here's something else. Okay, so the problem with this though is that IB run is going to take whatever here is replicated for all your different tasks. Well, how can you have, if you have more than 1 task per node, how can you change this yourself? Well, the easy thing to do is just have this being a script, and that script actually says, hey, which node or which socket am I on, or what's my task number, and I'll do something in terms of assignment depending upon what my task number is. Okay, so on a hardware node, you might have been given task 0 and task 1. How do you get that, which task you are, and how do you put it in a NUMA control to execute your A.out? And the secret behind that is you put, instead of this being here, you put a shell script here. We're going to call it numa.sh in the next page. And this guy is going to execute this and set up all this. So instead of your A dot out and here, which is going to have to do the same thing on each one, you just have a script, and inside that script, it's going to say, oh, if I'm task this, rank number this, I'm going to make my NUMA assignment. And so that's what's being done on this next page here. This guy, numa.sh, is going to go replace all this right here and this, okay? So that when that is, oh, and here it is right here. So IB run numa.sh, and actually it's using the argument there. You could put that inside there. Doesn't make any difference. As a matter of fact, I don't even think that's needed because it is used here. So that should be out of there. Okay, so basically our command is a bash shell script, and we're turning off all the MPI possibility of setting affinity for me. Don't do that. And then you get your rank here, okay? And this is a very long, complicated way of getting the rank, and I'm not going to explain it. And it's I know a much simpler way to do this, but you take this magic right side here, and that's how you get your my script on our system. Okay, lots of times the easy way is to know how the whether you're on when you're on a node, what your rank is by the node list, and it's about 5 lines of code to figure out your rank. So you find your rank, and in this case, what's being done is we want 6 nodes and we want 12 tasks, and the operating system is going to say, okay, I'm going to put 2 tasks on each of the nodes. Comes down here and it says, what's my rank? And it's going to be modulo 2, so it's going to be 0 and 1, and depending upon what your rank is, it's going to put it on socket 0 or socket 1. Okay, and then here's our socket declaration down here, and here's our NUMA control with the details that we want now. It's not going to have to be the same because we have this script. We can find out these environment variables, and now we can control for our particular rank which socket we're going to do and the forced binding we have up here. So that's the coolio about that. Okay, so that's 2 tasks, 8 threads, and so you can copy this. Another place that it's located is in this something very similar to this is in TAC affinity. So if you don't want to have to work that, and you just have something work with numa.sh, and you have something very simple, what you can do is just say TAC affinity, and TAC affinity assures that there's an even distribution for you for your task across the different sockets on the node. And in this case, we're going to have 4, and we only have 2 sockets, but you want 4. So it's going to make sure that you get 2 on one socket and 2 on the other, or whatever. If that number were 48, it do the same thing. It's going to evenly distribute that for you. And of course, if you increase this number, you decrease the number of threads. Yes.
Criticize.
Yeah.
So here I see like column out twice. One inside of the
Yeah, I said that wasn't necessary. Actually, it's going to ignore that. I don't. Yeah, this is. Or you could do pound, $1 to get the argument for that, but somebody just stuck it in there. So yeah, good point. Good point. Okay, and so you could use TAC affinity. That's the easy way to do it if you have something very simple. Okay, and what lots of people do is they'll try it, see if it works better, and they might be happy. And if it doesn't work better, then they're always going, why? And then they check their code and check. So how do you know where these are executing? You have a long-running job, and did you make a mistake and all the threads are running on one core? Anytime you have a job running, you can also SSH to that node or any of the nodes that you own. You just do a SQ-U username, and that will show you your listing for that job. And over on the far right, it will show you the nodes that you have been assigned to you. You SSH over there in a different window and run top, okay? And that will show you, what's executing there, but it's not going to show you the assignment. What you have to do is hit the 1 key, and you don't even have to do anything else. Just hit the 1 key, And now it'll show you all the cores and what their load is on the particular cores. And so now you can see which cores things are being executed. And of course, when your scenario with the number of tasks and the number of threads, you want them all to be lit up to 95% usage. And when they're not, then you're not using all of them. So that's a good way to check that out. So summary, you possibly need this. You will need this with hybrid jobs. You want to know about the core affinity and the memory policy. We now have given you the tool to specify the sockets and the core level control for positioning these, and things don't always work out that well. So sometimes there's an imbalance with things. We talked about that using OpenMP inside your code. Lots of times the schedule for for loops is static, but if there is imbalance, you might want to try using dynamic as the scheduling. That's sometimes helpful. And as a matter of fact, if you look at the code for the lab, you'll see in there where it's set to static, and you might try changing it to dynamic to see if there's any difference, or if there's, as they say, dynamic has lots of overhead. Sometimes it's not that bad at all. And different things can cause an imbalance of system. The operating system always has to have a core to run on. I/O is being done someplace. The daemons have to run someplace. So sometimes if things are gone awry in the background, core 0 might actually be the slowest running core for your application. And so there might be an imbalance there. So sometimes dynamic is the safest. You might have a little bit of overhead. Static usually is pretty good because static is cache friendly, as you learned in the previous. So here's what TAC affinity looks like. Again, it's a script, just like what you were doing in numa.sh, or what we were looking at before. And it's turning off things here. It's finding my rank, and then some things down there. But down here, then it's determining how many, this wayness, or the number of tasks per node. And it's coming down here and says, if my way is only 1, fine. If my way is 2, do this. And if my way is, let's see, equal to 2, and then else, if it's even ranked, then it's going to be setting this up modulo 2, setting across the different nodes around robin, the NUMA nodes. And then if it doesn't know what to do, it says, oh, just run any place. Okay, so that's what's happening down here, and here's your NUMA control command. They use an exec. Supposedly I believe that's more efficient. We didn't some time back, but I think somebody found that it works out better, or there's some specific reason. Don't know the details. Okay, so that's it. Only 9 minutes over. So what we'll do is start on the lab, and let me pull that up. So a couple things here I just want to point out. You download the tar. Not download it. You CD to your home directory. You untar the NUMA hybrid, and what you do is go down there and you do some operations that we show you. And actually, we're going to have you set some NUMA controls and then evaluate the timing for those, for the different ways of doing it. And you'll see that there are significant differences in terms of the speed, depending on how you do the NUMA control on hybrid code. And what we do is, in a serial section and a parallel section, you're running this operation, DAXB operation, and there's a make file, and you submit that job with SBatch. Okay, you could do this a different way, a little bit easier, maybe a little bit more fun. Do IDEV and look at the batch script in here, and it will say only give me 1 or 2 tasks, minus N2 or minus N1. Go and execute IDEV minus N1 or minus N2, depending upon which directory you're in, and then go look at the job script. change the job script, chmod it to 700 to give it executable, and now just interactively /job, and it will execute it for you. So that's an easier way than running batch, and you can grab lines out of there and execute them. But remember what's happening in the batch script when you're looking at this job, you're turning off, you're exporting environment variables to turn off the turn off the MPI affinity. And so if you're doing that interactively, you know, IB run interactively as opposed to running the script, you're just doing it interactively, set those environment variables first. So either way, it's good information. It's fun in that you coding is already done for you. You just make the file, run it, and then do the analysis. We ask you, well, what's running faster? Why is it running faster? And so you should know these things. And it's just about 3 pages of filling in tables, but I like it because it causes you to think. You have to think not only in NUMA control, you have to think not only about the hardware, of course, but you also have to think about the software and how that's done. If you want to see the configuration of the system, there's HW lock on, so you get on a node interactively with IDEV. Do you have to load that up with a module? I think you might have to. Module load HW lock, or it should be in your path, HW lock. And if you have SSH'd over there with the -Y, it should give you a display, or back and do a man on HW lock, and then it'll show you the details. You could probably do command line, and it'll show you a text version of it. But if you can have it display back, there's X display that's pretty good. Okay, so here's the lab. Go back to the first page and a CD and untar that file and have at it. If you have any questions, I'll be around.